Hi friends, today's class we are going to discuss about rotational spectra of diatomic molecules. The definition of rotational spectra is that the interaction between rotational energy levels of gaseous molecules and microwave radiation causes transition between the rotational energy levels by the absorption of microwave radiation is called a rotational spectra. That is, when a molecule absorbs microwave radiation, the interaction between rotational energy levels of the molecule and the microwave radiation take place. Then it causes the transition of rotational energy levels. The condition for rotational spectra is that the molecule must possess permanent dipole moment. The microwave spectra occurs in the spectral range of 1 to 100 cm inverse, and this microwave region lies between far infrared and the radio frequency region. Microwave spectroscopy deals with the pure rotational motion of molecules. It is also known as rotational spectroscopy. So the theory of microwave spectroscopy is that due to the rotation of charged molecules, induced electric field is produced, which interacts with the electric field component of microwave radiation. Molecules having dipole moment and their interactions will give rise to a spectrum. When transition occurs in rotational energy level, energy is absorbed and the peak appears in the rotational spectra of that molecule. We know that the microwave spectra is only shown by that molecules which have permanent dipole moment. So the dipole moment is the degree of polarity of a molecule can be expressed in terms of dipole moment. It is the product of magnitude of the charges and the distance between them, that is bond length. Nu is equal to Q plus L. Q is the charge, positive and negative, and the L is the bond length. In the previous video, we discussed about the expression for moment of inertia. So the second part is expression for rotation energy, that is allowed energy levels. That is given by the equation is equal to EHC J into J plus 1, where B is the rotation constant given by H by 8 pi square IC centimeter inverse. H is the Planck's constant and C is the velocity of light expressed in centimeter second inverse, and J is the rotation constant number that can take the values 0, 1, 2, 3, etc. We can substitute J is equal to 0, 1, 2, 3, 4, etc. into that equation. We get the allowed rotational energies of a rigid diatomic molecule respectively. That is 0. 0 means ground state, no rotation at all. So the next one is 2 BHC, 6 BHC, 12 BHC, and so on. Let's discuss about the selection rule for rotational transitions. The essential condition for a molecule to undergo rotation transitions by absorbing microwave radiation of a characteristic frequency and thereby yield its rotational spectrum is that it must have a permanent dipole moment. However, all possible rotation transitions are not quantum mechanically allowed transitions. So there is another selection rule to be considered. According to quantum mechanical principle, only those rotation transitions in which rotational quantum number J changes by one unit are allowed. All other transitions are forbidden. That is, only those rotational transitions are allowed for which delta J is equal to plus or minus 1. Here plus denotes the upward transition by absorption of energy and minus denotes a downward transition by emission of energy. The rotational spectrum of a rigid diatomic molecule, that is, only those rotational transitions are allowed for which delta J is equal to plus or minus 1. Here plus denotes an upward transition by absorption of energy and minus denotes a downward transition by emission of energy. The rotational spectrum of a rigid atomic molecule will consist of a series of equispaced lines such that delta nu bar is equal to 2b centimeter inverse. Here nu bar is the wave number. Then the intensity of spectral lines. All spectral lines do not have the same intensity. This is because there will be different number of molecules in each level, and therefore the number of molecules that undergo transition from different levels will also be different. The line intensity will be directly proportional to the initial number of molecules in each level. The factors that decide the number of molecules present in different levels, that is the population of levels, are given by Boltzmann distribution in the levels and the possibility of degeneracy in the energy state. Degeneracy is the existence of two or more energy states which have exactly the same energy. The first factor, Boltzmann distribution among rotational levels, is given by Nj is equal to N naught dot e raised to minus Bhc j into j plus 1 divided by Kt. Here, N naught represents the number of molecules in the ground state, j is equal to 0, and the number Nj in any higher state of j. The second factor, degeneracy factor, it can shown that the each energy level is 2j plus 1 fold degenerate. Thus, with increase in j, the molecular population in each level decreases exponentially, which shown by the previous Boltzmann distribution equation. By the number of degeneracy levels available increases. By combining the effects of both the above factors, we get Nj is equal to 2j plus 1 into N naught into e raised to minus Bhc j into j plus 1 divided by Kt. By differentiation of this equation and equating to 0 leads to that j value where the population is maximum. J is equal to root kt divided by 2 bhc minus half. The level with integral j nearest to the above value will have the maximum population. That means the transition originating from the level having the integral j value nearest will have the maximum intensity. The application of microwave spectroscopy is that it is used to determine the moment of inertia and the bond length of diatomic molecules. We can calculate the moment of inertia by using the equation I is equal to nu r square, where nu is equal to m1 m2 divided by m1 plus m2. It is known as reduced mass of the molecule. And the bond length of the diatomic molecule can be calculated by using the equation I is equal to root I by nu, where I is the moment of inertia and the nu is the reduced mass of the molecule. Thank you for watching this video. In the next class, we will discuss about vibrational spectroscopy. If you like this video, please do like, share and subscribe for upcoming videos.